How do you know your project's in trouble? Does it have a software component? Yes. Then it's in trouble. Wait, is it a software project? Well, then it's certainly in trouble. Greetings, I'm Dr. Will, and welcome to Dr. Will's Software Project Leadership channel, where we focus on building real software to solve real problems. As Tom Cargill says, the first 90% of the code accounts for the first 90% of the development time. The remaining 10% of the code accounts for the other 90% of the development time. If you've already subscribed to the channel, thank you very much. If you'd like more content like this, then subscribe and hit the bell below to be notified. Since the days when computers first came into common use, there have been tens of thousands of accounts receivable programs written. There are probably a dozen or more accounts receivable projects underway even as I speak. And somewhere today, one of them is failing. That's according to DeMarco and Lister in the book Peopleware. Okay, that's enough doom and gloom. Well, that's actually not quite enough doom and gloom, just wait. Like most entrepreneurs, I tend to be optimistic. I'm even known as Mr. Brightside because I always look on the bright side. Building software system can be daunting, especially doing it on a tight budget or schedule. And these days, what isn't done under a tight budget and schedule? The Standish Group Chaos Report found that only 29% of IT project implementations are successful. 19% of them are considered utter failures. The Standish Group finding isn't incidental either. Research by McKinsey found that 17% of large IT projects go so badly they threaten the existence of the company. In other studies, 25% of technology projects fail outright, 20 to 25% don't show any ROI, and as much as 50% need massive rework by the time they're finished. But why? What's so special or challenging or downright perverse about software that makes it so difficult to deliver a high-quality product on time and under budget? Well, here's why. First, complexity. No two parts of a software system are alike. No two parts of a software system should be alike. If they are, we make one of them into a subroutine and replace the other with a call to the first. You have orders of magnitude more states in the software system than the hardware that it runs on. Scaling it up is not just adding more of the same thing. It's not just the same thing bigger or more of the same thing, but rather an increase in the total number of all different things. There's a nonlinear increase of complexity with size, exponential growth in complexity. Second is conformity. Much of the complexity in the system is arbitrary. It's forced by human institutions and systems to which the software must interface. The software has to conform because it's perceived to be the most conformable. And because this complexity is the result of conforming to arbitrary external interfaces, it can't be simplified by merely redesigning the software. Here's an example. Back in the day, the United States federal government decided that every automobile that was sold in the United States had to have listed on its sticker the percentage of the parts that were made in the United States. No auto manufacturer tracked that information. Every auto manufacturer had to rewrite parts of their systems in order to track where the countries of origin were for the parts, and then figure out how to coordinate that information and put it out onto all of the stickers that are on the car windows when you go by them. So by a stroke of a pen, the government caused a lot of work in the IT departments in major auto manufacturers in the United States. Third is changeability. Software as a system embodies its function, and the function is the part that most feels the pressure of change. The software can be more easily changed, and all successful software does get changed. As it is found to be useful, it's applied outside its original domain. Take the spreadsheet, for example. The original spreadsheet was built to just add numbers together in cells. It's turned into a database system in some cases, and they're used to model business activities where complex corporate decisions are made based on unvetted and unverified spreadsheet models. Software survives beyond the normal life of its original hardware platform, perhaps far beyond the hardware it was originally written on. Finally, there's invisibility. Software is invisible and it's unvisualizable, if that's even a word. The reality of software is that it's not inherently embedded in space. Therefore, there are no ready geometric representations for it. Despite progress in restricting and simplifying software structures, they remain inherently unvisualizable and do not permit the mind to use some of its most powerful conceptual tools to manage it. Well, no wonder you feel overwhelmed. You should just put your project out of its misery. But seriously, this channel is dedicated to putting these things into perspective. Together we can't get rid of the complexity, conformity, and changeability, and heck, we can't even see the invisibility, but we can start making sense of it and unwhelm you. This channel is dedicated to helping software projects succeed, not just in the short term, but in the long. So if you'd like more content like this, then subscribe and hit the bell below to be notified when more content becomes available. Also, if you have any questions, complaints, concerns, issues, put them in the comment and we will entertain them later. That's it for me, for you for now. Have a great day and a great week. Be careful out there. I'll be seeing you.